Our spectators, showing on the screen there, our spectators are ionic on both sides. They're aqueous on both sides. Since everything over here is aqueous, I'm going to look over here at the products and see what's aqueous in the product side. Because if it's aqueous in the product side, it's part of the spectators. So that means my potassium is aqueous, and so is my nitrate. And since I balance the equation, I know that my 6 potassiums are going to be 6 over there. So I'm going to go cross out my potassium, cross that out. I'm going to cross out my nitrates over here as well. Okay, so the reason I picked those is because they were aqueous as products, and everything's aqueous as a reactant. And this was already balanced, so I knew that the numbers would work out. Then if I'm going to write my net ionic, I just look at the things I haven't crossed out again. So I have my 2 here, my Fe, and this is where I had said this had to be a 3+, because when we were figuring out charges, this was a -1 and there are 3 of them, so that has to be 3+. And on this side, it's aqueous. Reactants on these kind of reactions are always aqueous. And then over here, I have the oxalate. We said the oxalate was a -2. And I'm going to apply this coefficient. And if there happened to be a subscript around the parentheses, I would multiply them, but there's not. So this is going to be 3C2O4. And then on the other side, I should have either a liquid or a solid that I'm writing down. So it was liquid water over there. On this side, it's going to be the solid iron 3 oxalate. Now notice I said iron 3 oxalate, even though there's a 2 here, because that 3 tells me the charge of the iron. And it should be balanced. 2 irons, 3 oxalates, 3 oxalates. Okay, that's how we can get to our net ionic equation. All right, I'm going to skip anything. Okay, so we are going to look at several different kinds of reactions in this chapter. I believe it is section 2 or section 3 that lists them all out. There are a couple of different ways to organize them, but basically there's 5 types. Today we're going to look at double displacement, and we'll look at the others later. So we've just looked at 2 types of equations where we had a bunch of ions involved. These are both double displacement. One is called a precipitation reaction. It will have a solid product. And one is neutralization. It will have water as a product. And we'll get more details on those in just a minute. I just want to list out all of our different types. One type of reaction is basically you're putting a bunch of different ingredients into a pot and making one chemical. So we call that a synthesis. Or sometimes it's called addition. Those are the most common ways of referring to them. Sometimes you will also see combination. So I'm not trying to confuse you. It's just different places will call them different things. So I want you to have all the information. These are the 2 I use the most often. So if you call it, if I say what type is this and you call it any one of those 3, that's fine. If I tell you which of these is and use a term, it will be one of those 2 terms. Okay. Then we have kind of the reverse of that, taking one thing and breaking it up, and we call that a decomposition. So the reason we call it a double displacement instead of just displacement is that there's also a single displacement. So remember I told you the first reaction that we looked at was a single displacement. In a single displacement, there's not partners to switch. The double displacement, each compound has a partner and they can switch. But in the single displacement, there's an element. So there's no partner for it to switch with. And then we have another kind that we've seen, combustion. So we looked at methane on Friday when we were talking about balancing equations, that when it burns in oxygen, it produces water and carbon dioxide. So these two are what we call redox or oxidation reduction reactions. And they will always be oxidation reduction reactions. Numbers 2 and 3, sometimes are oxidation reduction and sometimes aren't. So sometimes you'll see this as a fourth category instead of 4 and 5. But it doesn't really help you with these that are sometimes oxidation reduction and sometimes not. So hopefully when we get to looking at all of them, I'll have you get those sorted out fairly easily. So we're going to look just at this right now, double displacement, how we can recognize it, how we can predict what the products are. Okay, so in a double displacement reaction, you're going to have 2 reactants and 2 products. So on this side of the board here, the names all are based on how many reactants and how many products you have. So this one's 2 reactants go to 2 products. We also have more information about the reactants. They are aqueous and they are ionic. We're going to throw acids in there because acids, especially strong acids, when they are aqueous, we're going to lose that hydrogen. And so they're going to behave like ionic compounds, having the H plus separate. So we can recognize these if I have 2 reactants and both of the reactants are ionic, metal and nonmetal, or if one of them is an acid. So how do I know an acid? Well, we'll get to that in just a second. Our products are going to include either a solid or water. I'm going to have a generic equation here. An ionic compound is a metal and a non-metal. I'm getting behind in this class. So that's the generic metal, non-metal. And then since I need a different metal, P is just going to be a different metal. It's not supposed to be lead or anything like that. It's just a different metal. And Y. And in order to predict the products, we're going to look at the outsides and the insides. Because our first element, the metal, can only be positives. So we can't put those two together because positives will repel each other. And the last 2 are negatives, they're anions. The nonmetals will also repel each other. So if I'm going to switch up partners, I've got to put a metal with a nonmetal. So I'm going to get the outside guys together. That's going to be one of my products. And then I'm going to get the insides together. That's going to be my other products. And then once we learn solubility rules, we'll be able to predict which one of those might be the precipitate or the solid. This is supposed to be an X. Yeah, that would be confusing. Sorry. For neutralization, you have an acid and a base. How do we know an acid when we see it? What's it going to have out front? Hydrogen. So like HCl, HBr, HNO3 is going to be H something. So it might just be an element like chlorine, or it might be an oxo acid. So like ClO3. All right, for a base, what you would know for a base is there's generally a metal with hydroxide. That's almost always the way we'll see it. So in lab, sodium hydroxide is the most common base that you will use. But there are 2 kinds that are a little bit sneaky, carbonates and bicarbonates. So MCO3 or MHCO3. What happens with those is carbon dioxide will leave. So if I take out a carbon and two oxygens, I'm left with one of the oxygens left behind, and it'll get together with the water to form a hydroxide. So it'll turn into a hydroxide after it bubbles off the carbon dioxide. So if I had HBr plus FeOH3, so this is the acid because there's an H there. This is the base because there's an OH there. And you had to predict the products. The products, and I should have said this, are going to produce water and a salt. The salt is just putting together the metal and the non. Okay, so the H and the OH are going to get together to form the water. So that's my outside. That's going to form water. Then my inside is going to form the salt. So in this case, since I have a 3 here, this tells me my iron is iron 3 plus. These are 3 negatives, so that has to be 3 positives. Bromine is a 1 negative, so I'm going to need 3 of those as well. And those would be my products. Now in lab this week, you're going to be doing something similar to this with sodium hydroxide and hydrofluoric acid, but you're also going to be doing a little bit of what we call stoichiometry. You're going to know something about the sodium hydroxide with a base, and you're going to try and figure out the concentration of the acid. So to do that, you have to balance the equation. So since I have 3 bromines here, I'm going to put a 3 here. Then that's going to tell me that I need 3 waters. So you're going to be able to figure out from the molarity and the volume, the moles of FeOH3. So that's going to be molarity times volume. You've seen that. You want to get to moles of HBr. So you're going to do just like we've done with other things, but we're switching chemicals this time. We want to get rid of moles of the hydroxide, and we want to go to moles of the acid. Where we get the numbers from is from the balanced chemical equation. So we'll use the 3 here and the 1 here. Now in lab, it's going to turn out to be a 1-to-1 ratio, so it's going to be a lot easier. But normally you're going to have to pay attention to what the coefficients are on the chem. Okay, we'll look at that in more detail on Wednesday.